And first I introduce the jury. The first is the Donghua University, Wang-Chi Professor. And Chung Lin Professor. I'm Vincent from the Republic of China, military academy. Now, the team A, you have 10 minutes. 你不是 A 吗？
我不选你。
哎，你不是刚选 B 吗？
没有，他刚以为他不知道，他刚不知道哪个要先报告。
OK。
Sorry。
好。好。Captain。这把这擦掉。OK。Team A, you have 10 minutes before you.
Hello, good afternoon, everyone. Our theme is a candle in water, and team name is team name. Yeah, we are team name. Okay. The belly flow is meaning candle can flow in the water, but also seem like to sink into water. Okay, add some weight to the candle such that it barely flows. Okay. And the candle burns, it may continue to float. Investigate and explain this phenomenon. Theory. During the candle burning, the decrease of weight equals the decrease of buoyancy. The top of part of above the water will gradually close to surface of the water. Long A times A times HB times G equals time long W times A times HF times G. Okay. Okay. HB is the length which is birth. HU is the initial length which is above the water. Right. A is the cross-sectional area of a candle. Okay. The top of part of above the water will gradually close to the surface of water. That's our candle. Right. Density. Initially less than 1. Final more than 1. Right. The density of the original candle which is added when is less than the water's, so it could float upon water. When the candle was burning, the mass of it would decrease, leading to the density increasing, and its density would be more than the water's. Although the candle's final density is more than the water's, it would float upon the water. That is, the wax oil would surround the candle, and this wax oil of extra equivalent buoyancy, making float. The way of and when we put a nail into candle and we put it on the scale, we can measure the mass. And we use tracker to analyze the length of the candle. The volume upon the surface is decreased when the candle is burning. Finally, water infects the wick of candle, which causes the candle below the second place, not melting into wax oil. Therefore, the candle will burn again, after wax oil in wick run out. The average of burning velocity. The burning rate is linear. In beginning, the burning rate is more stable because the system just burns candle. Then we can see the burning rate is unstable, but beginning and later are less the same. The candle can continue burn even the density of candle bigger than 1, and we think the system have uncertain factor which let candle stop burning. Water inflates the wick of candle here. Okay. This is the second place. Finally, water inflates the wick of candle, which causes the candle below the second place, now melting into wax oil. Therefore, the candle won't burn again after oil in wick run out. The radius of the wax oil part gets closer to a constant length, that it will continue burn downward until it penetrates. We investigate that the density of candle won't become more than the density of water, because the wax oil won't flow out to water and it looks like a bowl, so it would flow stably, like a bowl. We also observe that the candle will slightly flow upward of the surface of water. Our conclusion. The thin candle vs without weight. Even if burning out, its density is constant, which is less than water's density. Therefore, it will keep float. The weight can let density of the candle bigger than 1. The reason of the burning candle continue flow surrounding wax oil. The surrounding wax oil offers extra equipment by buoyance, so it can keep floating. Okay, thank you. See ya.
Okay, I'm from Team 姆咪色的红茶, and I'm the speaker of this subject, Zhang Banghan. And let me introduce you to my fellow members. This is Wang Yuanyou. This is Gong Huanxuan. This is Chu Junwei. This is Liu Hsing. And next. And the topic of our subject is weight time. And in this subject, we investigate the weight change of an hourglass. And let's go next. Okay, so this is the outline of our report, and you can see we have variables, assumptions, and something about our experiment. And never mind, we'll explain it later. Okay, next. And this is the variables. The control is what will remain the same in this whole experiment. And the independent variables are what we want to know, the parameters that influence our experiment. And we will investigate them later, okay, each of them. And if we investigate any of them, the others remain unchanged, okay. Next. Okay, so our assumptions are that the fall height impacts with an amplitude of peaks of our data in the read of our rate change, okay. And the total sand weight impacts the fall time, and the bottom texture impacts force exerted on the balance. And we assume that there's no bouncing for sand on collision to the bottom. Okay, so next. And this is our model. Yeah, it's our model. Okay. Back. Okay, so you can see we have two parts for the height parameters, and other parameters are there. We'll explain it later. Okay, and next. It's made by the blender. Okay. Okay, so what are the constraints of our experiment? The size and weight of each sand we cannot control, and there are collisions between the process of flowing sand, and we cannot control that either. And the flowing speed varies between trials, and the tension of the switch we use to control when the sand falls. Okay. And also, the sampling time interval of our mass measurement equipment is limited, and that restricts our precision of data. And next is our equipment. It's basic here, so if you want to see it, you can see it later. Okay, next. Okay, so next is the theory part. Okay. So, according to our theory, we expect the curve to look like this. So, our theory assumes that the flow rate is a constant, and there's no bouncing. Next. And that, we're going to explain why our theory is like this. So, before they drop to the bottom, it experiences a downward curve. Next. Okay, and the second state will experience a stable state. As you can see, it's a line, according to our theory. So the theory assumes that the flow rate is a constant. So the delta m divided by delta t should cancel out. So the read should be mg. Okay, so the read remains stable. That's our theory. Next. Okay, and for the finishing part, you can see that the sand in air gradually reduced. So there's already no sand on the upper part of our hourglass. And so there's only sand flowing down and decreasing. The sand in air is decreasing, and also exerting force on the balance, which will result in this upward curve. Okay, so this is our model for explanation of our experiment. This is the most significant model of our data. We use 300 grams sand and 2 levels of our hourglass. Okay, we'll explain each part of the graph later. Okay, next. Okay, so part A. At the phase of initial sandfall, you can see, I forgot to mention that we have defined some variables here, and we're going to use them afterwards. The sand variable f, the initial weight m0, sand air, which means the sand in air, and sand on the bottom, and the same mean force. Oh, it's cut off. Okay. And the read should equal, if we minus m0, it should equal negative sand air in this phase. Okay, thanks. And okay, so in part 1b, the initial sand that falls from the top hits the ground. So upon hitting the ground, it increases from the lower peak to up. Okay. And remember that in our theory, we said that the read is constant, but actually that's the result. So we need some correction to our theory. Okay, so why is that? During stable state, read has a tendency to be high. So our hypothesis, H0, supposes that sand doesn't bounce on collision. Where in reality, they do. And when they do, they result in impulse and adding up to a read. It adds up to a read. Okay, next. Okay, and why is that the stable state is not stable? Okay, so we have made a graph showing the flow rate of the sand. And as you can see, it has an oscillating tendency. And yeah, and notice this peak at about here. We'll mention it later. Okay, so why do they oscillate? Why? Okay, so our model explains it this way. So we didn't model with 15 degrees of 15 dihedral degrees before, and the result was the hourglass didn't work for us. So what happened in the 15 degrees model? So at first D1, you can see the salt volume D1 first falls down, as there's no support underneath, and losing support D2 falls down also, collapse. But for S, it didn't fall down. So the 15 degrees model wasn't working for us. So we used the 60 degrees model. And as an observation of our 60 degree model, we can see that when D1 first falls, there's a D2 that comes after it. So lose support, come down. And after D2 falls, D3 falls down, losing support of D2 and falls down. And it goes all the way to Dn, and you can see that the whole sand in the upper part will eventually fall down, but not in an even fashion. So you will experience oscillating fall rates. Okay. Okay. So why is there an apparent downward curve in the second stage? Why is it? So yeah, you can see. Thank you. You can see at this point we have experienced really fast flow rate near the end of the flow, okay, which corresponds to this. Okay, and next. Okay, this is the part 3 of our experimental data. Okay, so as you can see, sand, this part, the upper part, already has no sand, and the sand area is falling down, and eventually, as it hits ground, it will eventually get to 0. But at the same time, the impulse will add to the read of a balance. And you can see increase and eventually goes down. Okay. And next we'll compare our independent variables. Okay. Okay. So this is the model of the falling height of sand. So if we use a lower model to compare, the lower peak arrives faster, while the range of the read change is smaller, which can be easily solved because your amplitude corresponds to your height. That's apparent, right? Okay. And no. Wait a minute. And the higher peak has a smaller width and amplitude, as you have shorter fall time, and it will result in a shorter interval. And the next parameter is the 300 grams model and 200 grams model. Okay, so you can see for the 200 and 300 grams model, the lower peak arrives at the same time, and the amplitude is consistent between the groups. So it doesn't matter your weight. The first peak is the same, so consistent. So arrival time for the high peak is shorter for less weight. That is obvious also because less sand and you flow out of sand faster. Okay. And the third parameter that we're going to show you is the buffer texture. For a model texture, we use a paper plate underneath, but we're going to investigate what will be changed if we use different textures. With acrylic, you can see it is smaller in max.
Thank you. Team B, you have 2 minutes to show your question to A, and A have 2 minutes to your question to B.
We would like to see your part of theory and compare to your final results. Okay. Can you show us that? results. I mean, what flows and what sinks, that part of your conclusion.
Our conclusion is so our conclusion is sorry.
Just one. Answer the question.
Our conclusion is here. Okay. See.
Read it out. Just read it out. Just read it out.
If it is burning out, its density is constant, which is less than water's. Therefore, it will keep float.
Okay. So another question: how do you measure the density? How?
We measure the mass and the volume.
When do you do that?
Okay. 2 minutes. A to B.
Can you show your conclusion?
Okay. 我刚没修到这里。
Wait. Yes.
Okay. The thin air reduces Rhe as it doesn't touch it or exert force on the balance.
Wait a moment. This time your question, not conclusion.
Yes.
They asked me about the conclusion. Okay. And then volume exerts force on the balance, which causes Rhe reduction. And the variation of Rhe was determined by formation force, the value of thin air.
We have another question. Can you show page 12 or 13? The graph don't have any unite.
We're just trying to get out the tendency, as we don't know how long it takes for that's just the theory part. So we're just trying to explain the tendency we suppose it is supposed to be. We have to do an experiment to be sure how long it takes to be to flow up for the sand flow.
Okay. That's all.
Okay. 2 minutes. Yeah, ask the
So first of all, we would like to ask you the definition of your disk. How do you calculate it? I mean,
We measure the mass and the volume. We mass divide volume.
I mean, it's floating and burning, but how do you measure when it is burning? You take it out, or if you take it out, it does something on the experimental results. So what do you do?
We use tracker to analyze the length.
The length. So you suppose it is a cylinder.
Okay, wait a minute.
And another question about your hypothesis and your final results. I mean, the pictures you take. So in your theory, you said that the initial candle is like this, and it goes down eventually. And your picture shows us the other way around. So why is that?
I'm so sorry. Please say again.
The up and down of your candle in your theory and your picture is different. Why?
That is another Oh, this is a white candle, and because it.
Okay, another question. So, how about some parameters of your candles? Do you have them? Any data?
Okay.
Wait a minute.
Here.
Okay, that's right. It's close. We can see it. And how many times have you done your experiment for each result? I mean, your curve. Do you try the experiment times, or is it just a few times?
About 22 minutes.
So you get the average, or what?
Yes. The density.
And also page 6. Okay, so you say the initial is less than 1, and the final is bigger than 1. So why is that? The final you said it will flow, but a density of bigger than 1 shouldn't flow. It should sink. Why is that? I mean, is there some special definition of your density?
Because we add some nail, so the mass will bigger.
I know it's bigger, but it should be at least. And how about the factors that influence?
Because the wax oil surround the candle, so it offer extra buoyancy.
So you say there's a local
Okay.
factor.
Comment.
If you change the sand into water or other liquids, the result will identical or not.
You mean change that?
Change sand into water or other liquids.
Well, no. Short answer, no. But what do you want to know? What do you want to know how it affects? About what parameters do you want to know?
We want to know why. Okay. What is different in different liquid, sand or water?
We think that it's like dividing things. So the more divided the flowing substance is, the result will be better. So less oscillation of it. So you remember that we showed a graph showing that it oscillates while flowing. If it's a liquid or something that it doesn't have big chunks.
Show the data again.
Okay, 直接看，给他看那个我们。Yeah. Okay, this one. Okay, so we can see. So the salt volume collapse if the previous supporting volume collapse. But in water or other more divided substances, it won't happen. But if it's big chunks, it's more likely to happen. That's what we think.
What the scale you use in the experiment?
You mean the balance? 你说磅秤吗? Oh, the balance is in word first. We have a picture of it. Okay, so that's it.
If you change spring scale, what it will happen?
You mean? We think there will be more oscillating. So we didn't choose this because we think will affect our results. Because if we have to do that, we have to divide the components into multiple components, and there will be an error between springs.
If you change the radius of neck,
You mean the Hsing? You mean this one? The 2 cm?
Yeah.
It changes flow rate. The flow rate, yeah, it changes the D1 sub volume in the previous graph. It changes the D1. So it changes the value of the first lowest peak.
what do you see the data will bigger or smaller?
What do you mean? What parameters?
If you change the radius of the neck is bigger than.
Bigger than it is, right? Okay. So if that happens, more cells fall in the initial stage. So the D1 is bigger. So you will experience bigger peaks. So you remember the first one in the initial stage? You will experience a bigger one.
Okay, that's all.
Anytime you just your one man is your captain capacity. Okay. Now the Team B you 2 minutes.
Okay. Okay, so as of your team, we discovered that several of your definitions are not that clear. And also, you don't have variables, like we have control variables and independent variables. Maybe you should add some and tell us about it. But the picture is nice explanation. You still didn't explain clearly why your theory is different from your actual results. Oh, and the meaning of your density is kind of weird, but overall good. Okay, as of our team, our approach is mainly like we think what will happen, and we try to figure out if that really happens, and change each of our parameters, aforementioned independent variables, and try to see what happens. And we analyze how each parameters affect the results. And our model presentation was more clear. I think maybe you should try to make a model.
Okay. Then Team A, you 2 minutes to conversion.
Your presentation is too many words, and your data is to your experience device only one.
The texture is a control variable.
And your data is very good. Yeah. We think we can use more rigorous device to measure volume. If the width of candle bigger than constant, it is well difficult to measure the curve. Yeah. Thank you. That's all.
Okay. Juries, we have 5 minutes. Any questions? It's
Okay, F1, I have a couple of questions actually for this game. Which is your main reason for this? Can you show the data that you have a dip in the measurement?
You mean the
Yeah, that one? Yeah, this one.
Which
right.
which? This one?
The dip.
The first one or the second?
The second dip, which is your reason? Is the bouncing of the sound, or is it because of the higher falling speed?
It's because of the higher falling speed.
It's the higher falling
The
speed.
the constant. You see. So
Okay, fine.
you see a tendency to.
Yeah. Okay. Then why you don't see the 200 gram pace? The 200 gram pace, you do not see the second dip. Why? It doesn't have this higher falling speed.
Some of the data shows it has, and
Some of the data does.
I mean like most. So we think it is significant.
So it's not a general case.
We think it is because
Then
within
why
that,
you don't have it in the 200 case? What is your explanation?
because of as we mentioned previously, the constraints of a model, the sampling rate, interval time rate is restricted of that balance. You can't measure
You think it's
it
because of the
with
measurement?
resolution that clear. So we use the
Thank you.
okay. Timothy, please you explain what's the oscillation.
You mean what do I mean by oscillation?
Yeah.
I mean just the oscillation of the curve. I know it's not a too precise word for that. Okay. I mean like this part. And on some of our data,
Okay.
the second region.
Timothy, did the temperature will influence your result?
We think no. The answer is no.
Okay. Thank you.
Maybe two more questions for today. I saw from your photos, your panels seems to touch the wall of the glass. Did you have any experiment that the panel is in the center part? Did you have any cases like this that it doesn't touch the wall of the glass?
We just think the show the photo, so we
Right, I mean like this one, right? It's touching the glass. Right? Do you have any case that it doesn't touch the glass? This one doesn't touch. And do you see different result between these two cases?
Same one.
Right? Oh, this doesn't touch you, you're saying?
no.
Ah, okay, it doesn't touch.
Doesn't.
What about the shorter, the white candles you saw? You show 3 pictures. Do they touch your glass? Yeah, like this one, for example. Do they touch the glass or no?
No.
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 You sure them?
No, I'm sure.
Okay. Thank you.
Okay. And the students, please show your score. Team A, 656. Team B, 767. Thank you, everybody. 好，谢谢大家。